sequential decision making, which Matt Weinberg is going to address in his talk in the afternoon, are going to be talks today. Tomorrow, Sefi Naur will talk about online algorithms, and then Nikhil Bansal and Adam Weirman will talk about connections between online algorithms and queuing models, stochastic scheduling models. On Wednesday, there'll be 3 talks actually on the general sort of umbrella of machine learning. The first talk will be by Eli Upfal on sampling approaches. The second talk by Niccolò Cesabianchi on online learning, and the third one by Yishai Mansour on reinforcement learning approaches. On Thursday, we'll talk about something a little different, but very intimately connected with the program. The question of how do you analyze algorithms beyond the worst case. And a lot of the stochastic models are somehow lying between the average case and the worst case. And here there'll be 2 talks. The first talk in the morning by Tim Roughgarden, and the second in the afternoon by Kevin Leighton Brown, giving slightly complementary ways of viewing the area. And finally, we'll talk about some applications, and these are just 2 of the applications which might arise. The first talk will be by Anna Carden on algorithmic mechanism design, and the second one by Adam and Iran on applications of stochastic optimization and, in general, algorithms under uncertainty to energy problems. So that's the general framework. And each of these talks can be viewed by itself. It can be viewed. It should be viewed as part of the whole, and it should be viewed as ways of either reminding yourself of what you already know, learning something new, making connections. Hope you have a good time. So that's pretty much it from me. Stefano has a couple of words to say.
Just quick information on the additional information on the bootcamp and the organization of the program. So the bootcamp will also have 3 sessions of lightning talks. These are short 5-minute talks that allow the program participants to present themselves and to highlight the research directions of potential employees. So if you like to give a lightning talk, please send me email by today. Then for the activities of the program, of course, we plan several activities. We plan seminars, we plan open problem sessions, we plan additional activities. We'll also encourage you to send us ideas for reading groups on more specialized emerging topics that you like to discuss and to learn about. So if you like to propose a reading group, please contact us. And we'll have an organizing meeting next Wednesday in noon, where we will discuss all the activities that we like to carry on in this semester. So thank you very much again, and I guess I can give the floor to Vish.
Okay, so the first talk in the session is going to be by Kamesh on stochastic optimization.
Thanks, Vishy, and thanks, Anupam and Stefano for inviting me here. So the topic of this tutorial is stochastic optimization. Different people mean different things when they say stochastic optimization, and for the purpose of this talk, it's good to think about stochastic optimization as essentially you want to design an algorithm, but your inputs, instead of being deterministic numbers, are distributions. So just to give some context, there is this broad area of research called Markov decision processes. In a typical Markov decision process, you are given some set S of states, some set A of actions, and if there's a system, and if the system is in the state S, and if it has a choice of actions to take, if it takes action A, then it earns some reward that's denoted that RA of S. It's drawn from some distribution. The distribution is known to the decision maker, and the system transitions to a different state Q, and it could transition to one of several states. The probability with which it transitions to state Q is given by this quantity, which is indexed by the action, the previous state, and the next state. So it's in this state. You take an action A, it transitions probabilistically to a different state, and it yields some reward drawn from a distribution. So what is the input to such a problem? You're given the states, you're given the actions, and you're given the reward distribution for each state. You're given these state transition matrices. What are the probability for every state, for every action, and every next state? What is the probability that you will transition to that next state? You're given some start state of the system S. You're given some time horizon T, so you can make a sequence of T actions. And what you want to do is maximize the expected reward that you get over these T steps, right? And the expectation is over, the rewards themselves are stochastic in every state. If you take an action, the reward is drawn from a distribution, so there is some expectation there. And also what state you transition to is also stochastic, so the expectation is over all this stuff, right? And so what do you want to design, right? You want to design what is called a decision policy, which is a mapping from states to action. If I am in this state, what action should I take? Right? And this is sort of ancient. It is 60 years old. It is well known that, in fact, the whole area of dynamic programming was invented in this context by Bellman. And so the optimal policy can be computed by dynamic programming. It takes time which is polynomial in the number of states, the number of actions, and this time horizon. The reason I'm being brief here is that I'm not going to focus on dynamic programming in this talk. So in this talk, what we want to focus on is there are several problems, and I'll give you many examples of this, where either the number of states is exponentially large in the natural problem parameters, or even if the number of states is small, the number of actions can be exponentially large, right? And in this case, if you do dynamic programming, it will take exponential time. So the question is, for such kind of problems, can we design decision policies that are simple? So they may not be optimal, but can we show they are approximately optimal? And they should be efficient to. It should be efficient to find this policy, and it should also be efficient to execute this policy. So I'm keeping it high level for now. I'll give you very concrete examples as the talk goes on. If at any point you have questions, please feel free to interrupt me. Okay. So there are this field of stochastic optimization, there are a lot of problems that people have looked at that fall under this umbrella. If you can take any standard covering or ordering problem and define a stochastic version of it. I mean, so there's stochastic set cover, there are variants of stochastic set cover. Then you can take any scheduling problem and define a stochastic version of it, where the input, instead of the length of the job being a fixed number, it's a distribution. Hey, you have a stochastic version, right? You can have stochastic naps. I mean, take any sort of traditional optimization problem. I'll show you a stochastic version of it. Right? And another well-studied area, and there'll be talks on this later on, is auctions, and even you can view auction design as a stochastic optimization problem. So given that this is like this big laundry list, I don't want this talk to become a laundry list. So that's why what I'll do is I'll show like one overall technique or a class of techniques that fall under the framework of you want to design linear programming relaxations for these problems and design rounding algorithms for them. Right? So these things are well known for standard approximation algorithms when your inputs are deterministic. Can we develop such techniques when the inputs, instead of being deterministic numbers, are distributions? Okay. And that way the talk will become more coherent. So I'll divide the talk into 4 parts. The first part will take up this hour, and the second, third, and fourth part will take up the next hour. So in the first part, I'll focus on an extremely simple decision problem. I'll call it the maximum value problem. And using this, I'll illustrate the basic concept. I mean, what is a policy? What is a decision tree? What is an adaptive policy, non-adaptive policy? I mean, I'll sort of describe these terms in the context of this very simple problem. And we'll show how to design non-adaptive policies. I mean, this is just a term for now. And then I'll show you how to use LP relaxations, how these LP relaxations can be rounded, and what is the role of duality. I mean, whenever you have an LP, you can take its dual and get something from the dual. And in stochastic optimization, often the duals are extremely nice. That will be the first part of the talk. It will take up this hour. And the first part will be more like a classroom lecture. So in the end, you would have at least learned something. In the second hour, I'll do part 2, 3, 4. Here, I'll sort of have to define the problem and present the high-level algorithm, but I won't have time to go into any proofs and so on. So the second part, I'll sort of generalize what I did in the first part to what are called weakly coupled LPs. So which is basically a general technique for developing these LP relaxations. And the property of these relaxations is that they have very few constraints. And that will somehow be important when we have to do rounding. And examples of these, I mean, these are very well-studied problems: stochastic knapsack, stochastic matching, and multi-item pricing. So I'll do all these three. And the third sort of general technique is again very related to linear programming. Is essentially whenever you have a distribution, you can think of sampling from the distribution, right? I mean, so what does sampling buy us? Right? So you can. If you take the entire distribution, maybe the distribution has exponential size, so you can write some exponential size LP. But then maybe this LP can either be solved efficiently by sampling, or you can do something else using sampling, and that makes the running time polynomial. So I'll present examples which are sort of this multi-stage optimization and Bayesian auctions and how to solve LPs online. I mean, these are just terms for now, but I'll describe all these problems. And the final part of this talk will be on scheduling. The aspect that comes up in scheduling is this aspect of time. I mean, whenever you think of a scheduling problem, the crucial aspect is decisions have to be made over time, right? And everything I'll do in the previous parts, somehow time is there, but we'll never really use time in any sort of non-trivial way. But when we do scheduling, you have to use time in some non-trivial way. I'll present two techniques. Firstly, I'll show one technique which involves developing stronger LP relaxations with more constraints and more variables, maybe even exponentially many constraints. And the second technique is just, okay, if you have a complicated problem, just try greedy, right? And I'll show you, a beautiful result that is from operations research called the Gittins index theorem. Right? So that's the overall high-level picture of the talk. And important disclaimer, many of you work on these problems. I can't cover everything, so I'm sorry if what you work on is not covered. So in the first part, I'll define a very simple decision problem called the maximum value problem. It's closely related to something called profit inequalities that Matt is going to cover, but I'll present it very differently. Okay, so in the maximum value problem, think about there's a gambler. He's shown n boxes. These boxes are closed. The boxes are in front of the gambler. What the gambler knows is that the box J has a reward. It's drawn from distribution xj. The gambler knows xj, but the box is closed, so he doesn't know what value is there inside it. And these distributions are independent. So x1 is independent of x2, which is independent of x3. Okay. So this is the gambler. There are 5 boxes. They are closed. The gambler knows these distributions. So what he can do is he can open a box. Say he opens box 2. He sees there's 20 inside. Now, given that he knows this is 20, he can decide to open some other box. Maybe he opens this 3 and so on. Right? So the constraint on the problem is that he can open at most k boxes. Okay? And the final payoff he gets is the maximum value that he observes in any of the boxes that he opens. Okay? So he can adaptively open k boxes. Depending on what he has opened so far, he can decide which box to open next, right? But the constraint is that he can only open k boxes. And at the end of the process, he looks at the boxes that are opened, he picks the maximum value, that is his payoff. Okay. So as an example, suppose you have 3 boxes. Gambler can open 2 boxes. So these are Bernoulli. So this is x1 is 50 with probability half, 0 with the remaining probability. x2 is 60 with probability 1/3, 0 with the remaining probability. x3 is deterministic, 25 with probability 1. what should the gambler do? So suppose he opens the first box. Okay, he observes 0 with probability half. Okay, and now he has to open some other box, right? And whatever he sees there will be his payoff. I mean, this was 0, so x3, this guy has payoff 25. This guy, if he opens, has payoff in expectation 20. 25 beats 20, so he'll open this box, right? And he'll get 25. This is deterministic. Okay. Now with the other half probability, he would have observed 50. If he observes 50, if this box already has 50, there's no point in opening this box because 50 beats 25, right? So he'll open this box, right? If he opens x2, with probability 2/3, he would have seen 0 here, in which case his payoff would be 50. Which probability 1/3, he'll see 60 here, so his payoff will be 60. So this is like an adaptive decision tree, right? So this is one possible policy for the gambler. Open x1 first. If you observe 0, open x3. If you observe 50, open x2. Now suppose you have n boxes and you can open k, then just the description of the output could have size which is exponential in n and k. So this is the output of the problem. Okay. So the output itself need not be polynomial size. Okay. And the sort of expected payoff of the gambler will be the expectation of this guy. So it's 25 with probability half, 50 with probability 1/3, and 60 with probability 1/6. So it's 39.167. So now the goal is to find that decision tree whose expectation is the largest. Okay. Clear? And the inputs are these distributions. Let's assume they're discrete distributions. They have small support, so the input is polynomial size. Good. So one thing is, we can think of a non-adaptive policies that are simpler to specify. At least the specification is polynomial size, which is just choose k boxes up front without even opening them, and just open these boxes and take the maximum value. Right? Just pick a subset k of boxes. So now find the best subset k of boxes to pick such that the expected value of their maximum is as large as possible. So in this case, the best solution would be to pick x1 and x3 up front and open them. In which case, with probability half, the payoff is 50. With probability half, it's 25. That is 37.5. But the adaptive policy that decides to open the second box after observing what was in x1 does strictly better. Okay. So an adaptive policy which can have exponential size could beat a non-adaptive policy. Okay. So that is adaptivity versus non-adaptivity. But there's a subtle point, which is that the 37.5 is not that much worse than 39.167. They are pretty close. In fact, I'll show you that they'll always be close. Good. So what is the benchmark? So the benchmark we are comparing against is, as I told you, the value of the optimal decision tree. Okay, and let's call this value opt. It can have size which is exponential in k. So our goal is to design a polynomial time algorithm that produces a polynomial size decision tree that approximates opt. Okay, so this is the approximation algorithm's angle to the problem. Okay. Is it good? I mean, if you have questions, just interrupt me. I mean, I have background in approximation algorithms, but I know many of you have backgrounds in different areas. So if some of the terminology is not clear and stuff, just let me know. Okay.
So you're not restricting to non-adaptive policies yet.
No. So I'm comparing against, I'm comparing against this optimal decision policy. I mean, what I design may be adaptive, may not be adaptive.
So later you will tell us what's the ratio between adaptive and non-adaptive?
I'll tell you, yes. So in fact, the outline for this part will be, I'll present approximation algorithms for this problem. I'll first show you, suppose you were just restricting to the space of non-adaptive policies, how do you compute an approximately good non-adaptive policy? Then I'll show you LP relaxations for the adaptive policy. Then I'll show you the gap between the adaptive and the non-adaptive policy. And since this is a tutorial, just ignore the constant factors. I mean, sometimes it'll be large and you might cringe, but they can be improved, and that's not the point. And I'll show you in the second half of the talk, I'll show you more applications of this, and I'll show you other relaxations and so on. Okay, non-adaptive. So suppose our benchmark was not the optimal adaptive policy, but the optimal non-adaptive policy. Then can we design an algorithm that competes against that? So what is a non-adaptive problem? So given a subset S of boxes, which you have not opened, if the gambler just chooses S and opens them, then the payoff that he will get will be the expected value of the max of these distributions, just by definition. Now you want to find a set S of size k that maximizes the expected value of the max. Okay? And the basic idea is that, okay, this is a set function, you have a cardinality constraint. Maybe there's some property of this set function that will help us. And there's a well-known property called submodularity. For those who haven't seen it, what submodularity means is simply it simply means that diminishing marginal returns. Okay, so you're given some set function S, f. Okay, take some set S1, take another set S2 which contains S1, and take some element T which doesn't belong to S2. Okay. Then think about adding T to S1 and look at how much the function value increases. Think about adding T to S2 and think about how much that function value increases. Okay? The increase is larger for the smaller set. There's just diminishing returns. If you already have a large set, adding one more element doesn't increase your function value that much. Okay? So this is like sort of the discrete analog of diminishing returns. Okay? And the way this is defined, I mean, there are no other constraints on this f, but we'll need two other constraints. We need this function to always be non-negative. We'll also need this function to be monotone in the sense that if I have a larger set, the function value also increases. Okay? And so non-negativity and monotonicity are trivial for this function. If I have a larger set, the expected value of the max is only going to increase. That's straightforward. And this function is non-negative, assuming these xi's are non-negative. Good. So why is submodularity interesting? If I have to maximize a submodular function subject to a cardinality constraint that the size of this set I pick has to be at most k, then there is a well-known greedy algorithm for it, which just does the most obvious thing, which is start with the empty set. Okay, while the set has cardinality less than k, just pick that element such that adding that element to S increases the value the most. Okay, add that element, continue. Okay, just at every point in time, just add the element which gives you the largest increase, keep going. Right? There's a classical result due to Nemhauser, Woolsey, and Fisher that this greedy algorithm is not optimal. In fact, maximizing a submodular function subject to a cardinality constraint is hard to approximate. But it's a 1 minus 1 over E approximation, so it gives you 63% of the best possible value. This number is actually optimal. It's NP hard to get any. It's under some complexity theoretic assumptions, it's hard to improve this. There's nothing special about the cardinality of the set being of size k. The different elements could have different costs, and there could be a bound on the total cost. There could be other constraints on what set you can choose. Variants of the greedy algorithm will work for all of those. And that's a big line of research in itself. Why is this result interesting? The maximum value, the function is actually submodular. And the proof is, and this is like sort of a very simple proof, and this proof applies more broadly in the sense that if you have a stochastic function, you want to show it as submodular, this outline will pretty much work, right? Which is, just look at the joint distribution of these, look at this joint distribution. Right? What you'll do is just argue submodularity sample by sample. Take some sample from this joint distribution. Okay, it's a sample of values for this guy, for this guy, for this guy, and so on. So take some sample of values you could have observed in the different boxes. Okay, for this sample, the value of the function is simply the max. Okay, so now these are not distributions; they are just some numbers. I give you n numbers for any subset. What is the maximum value of those numbers, right? And now, if you just take this function, right, it's very easy to check this is submodular. If I have a larger set, adding another value will not increase the max by that much. Okay. But this function f of s is simply the expectation over all samples of this guy, right? is the expected value of the max. You can write it as the expectation over all samples you could draw of the max of that sample, right? And now this submodularity property, this submodularity is like a sort of, it's a linear condition. So if I just take expectation, right, the inequality is preserved, right? You can take expectation of everything and the inequality, the direction of the inequality won't change, right? And that's the whole idea, right? I mean, that submodularity is preserved. It's just a linear condition, so it's preserved under taking expectations over all the samples. And in fact, in this proof, I mean, we didn't use the independence of these random variables anywhere. I mean, these could be correlated. The whole thing is still submodular. In fact, if you were to design a non-adaptive policy, it's okay for the random variables to be correlated. Okay. So if we want to compete against the optimal non-adaptive policy, what we have shown is that if you just implement the greedy algorithm, which at every point in time adds that box, which increases the expected value of the max the most, then what you will get is 63.2% of the value of the optimal non-adaptive policy. Okay. That is what the greedy algorithm gives us. And there are a lot more things that are submodular. I mean, you could have payoff instead of from one box, you could have payoff from many boxes. It's still submodular, same idea. In fact, you could think of minimizing the minimum value, and it turns out the log of that is also submodular. And in fact, submodularity, if I give you a network and I have a seed, I infect a subset S of nodes and look at how far the epidemic spreads, right? Under most random models of how epidemics spread, the expected size of the set of nodes that get infected will be submodular. Is a submodular function of this, what you infect. Right? In fact, if I give you a set of random variables and take any subset of those random variables and compute its discrete entropy, the joint entropy, that will be a submodular function of the set of random variables you chose. Okay? It's not true for continuous entropy, but it's true for discrete entropy. And these things have applications in the sense that they are real world problems that are solved by this kind of stuff. But that's all I have to say about submodularity and non-adaptive policies. I'll later on show that a non-adaptive policy actually approximates the optimal adaptive policy. That will come later. Okay. For now, we were just comparing against the optimal non-adaptive policy. Okay. Good. Adaptive. And here we'll use linear programming.
Question about non-adaptive. Is it the best bound? I mean, it's best bound for arbitrary submodular function.
I don't know if it's the best bound. So all we have shown so far is that it's NP hard to compute the optimum. But beyond that, maybe it's possible there is a PTAS.
And in the greedy algorithm, when there's dependence, you take the expected condition.
So it might be hard to compute. I mean, computing the expected max might be hard, but if you sample, I mean, you can, maybe if you sample enough from the distributions, you can approximate it. Okay. So what is the idea behind linear programming? Take the optimal decision policy. We don't know what it is. It adaptively opens some k boxes, and it obtains payoff from one open box. It's like some such decision tree. Okay. And we'll define some variables based on the behavior of this policy. And these variables, the important thing about these variables is that they will only be confined to one box. Right? I'll define variables separately for each box. Right? Because if I put all the boxes together, that will again have exponential complexity. I don't want that. So it's a relaxation. So we can define a variable yj, which is take this decision policy. It does something and maybe it opens box j, maybe it doesn't open box j. Right? Over its decision tree, what is the probability that box j is opened? Call that quantity yj. Let zjv be this thing, probability that the policy opened the box j, it observed value v, and that was the final payoff of the policy. That among the boxes it opened, that was actually the largest value.
So are all distributions now discrete?
Let's assume for now they are discrete. The way at the end you'll see that it doesn't really matter that the distributions are discrete. I mean, the final policy will be so simple that it will even work for continuous distributions. And in fact, the way I'm writing this LP, it will appear that this thing is discrete, but you can define the same thing for continuous distributions. It will all be fine. Okay. So just as an example, this was our optimal policy for this example. The policy always opens box 1, so y1 is 1. So y1 is the probability that the box is open. So the policy opens box 2 with probability half if it takes this branch. So y2 is half, similarly y3 is half. So if I look at the z variables, z1, 50 is the probability that the policy opened box 1, observed value 50 and chose that payoff. That would happen here. So that would be 1/3 is the probability. Similarly, z2, 60 is the probability the policy opened box 2, observed 60 and chose that. So that will be 1/6. z3, 25 is the probability opened box 3 was opened, its payoff was 25 and that payoff was chosen. And that is half. Okay. And if I give you a big decision tree, it's a bigger computation. The point is we are not going to do this computation. These are just some variables. Okay, okay, good. What will we do with these variables? So the basic idea is we want to write an LP that captures the behavior of this optimal policy, and we'll use these as the variables. I mean, these variables are insufficient to capture the entire structure of the optimal policy, and we don't really want to do that. Right? What we'll end up with, I'll show you that it will be a relaxation in a certain sense. And what we'll do is we'll understand the structure of this relaxation, convert it into a feasible policy, and show that it's an approximation, bound the adaptivity gap, and so on. By adaptivity gap, I mean the gap between the adaptive and the non-adaptive policies. So that's the basic idea. Okay, so we have to write an LP, so let's look at, okay, what constraint should we put? So let z be it's a random variable which denotes, okay, which box did I obtain payoff from? Okay, and so zjv is the probability that the box from which I obtained the payoff is j, and the value xj was actually v. Okay, good. So for this event to happen, that I obtained payoff from j and xj was v, two things must have happened, right? The policy must have opened this box, and the value in this box must have been v. Right? I mean, a third thing must also happen, which is that this v was actually the largest value. But let's ignore that, right? I mean, for this event to happen, at least these two events must have happened. More stuff must happen, but let's ignore that more stuff. Okay. But here is the important thing, right? That these two events are independent. Since the values in the boxes are independent, the behavior of the policy till the point where it opens box j will be independent of what it's going to see inside box j, because box j has a value which is independent of everything else in the system. Right? So this event, that box j is opened by the policy, is independent of what value is there inside that box. Cool? So I can multiply the probabilities of these two events. That's the important thing. So this value, since is at most the probability that box j is opened and I observe this value here. It must also be the maximum value that I observe in all the boxes, but it's at most this, right? And these two events are independent, so I can just multiply them out. But the probability that the box j is opened is exactly this value yj that I have defined. Okay, and let's call this is just the density function of what is inside box j. Let me use the standard notation for density function. Let me just call it fj of v. It's just some notation. So this is not a variable, this is something that's specified as input. Okay, that's the density function. I don't want to keep writing this quantity. Okay, good. So zjv won't be equal to this guy, because what we are not encoding here is that v was actually the largest value that the policy observed. This is sort of a relaxation. Good. That gives us one constraint. Is it clear? This is this constraint. Okay, what is the other constraint, right? So what is ZJV, right? ZJV is the probability that the payoff was obtained from box J, and the value that is obtained is V. But the policy can only get payoff from one box and one value of that box, right? So which means that by linearity of expectation, all these ZJVs must sum to 1. Right? Because the policy always, regardless of what decision path it takes, it's only choosing one box and one value. Right? So these must sum to 1. So what we are essentially encoding, this is like an expected value constraint. What we are saying is that the expected number of boxes from which the payoff is obtained is 1. We are not encoding that on every decision path the payoff is 1. Only one box is chosen. If it's true for every decision path, it's also true in expectation, and the expectation is what we are capturing here. In the same way, the policy opens at most k boxes on any decision path, so that must be true in expectation. Look at what is the expected number of boxes that it opens. The probability that j is opened is yj. If I sum this, that will be the expected number of boxes the policy opens. That must be at most k, because on any decision path, the policy opens at most k boxes. So whatever is true on any decision path is also true in expectation. That's all we are saying. Okay. And in this number is a probability. And if I encode this lies between 0 and 1, it also encodes this lies between 0 and 1 because I'm multiplying it by a fraction. That's it. And now what do we want to do? We want a policy with the largest payoff. So the payoff of any policy is just again by linearity of expectation. If it opened box j, saw v, and chose that value, the payoff would be v. So I just multiply that and sum it over all possible j's and v's. So I want to maximize this guy subject to all these constraints. So now I have a linear program. It has reasonable number of variables and constraints. There's the number of j's is polynomial. The number of j's is n. Number of values per j is small. Let's assume that. And there are only 2 constraints really here. That's it.
So you don't need positivity for z.
Yeah, z needs to be positive. Z will be positive because I'm maximizing something here. So. Yeah, I've written papers where I've dropped constraints like this and the reviewers point it out. But yeah, I should have written all those constraints. Yeah. Okay. So here is a simple example. Suppose I have 2 boxes. There is 2 with probability half, 0 with probability half. This box is 1, 0. And suppose k equals 2, so I can open both the boxes. Right? In which case, any LP solution is just going to set the probability of opening this box to 1, the probability of opening this box to 1. So those constraints are trivial, right? But still, this LP does something weird. Okay, what will the LP do? So what is this LP, right? So let's call this guy ZA2, which is like so this is box A has value 2. What do I do with it? This box B has value 1. What do I do with it? Right. So the LP says that okay, the probability that the expected number of boxes I choose is 1. That is this constraint. Now ZA2 is at most the probability that this guy had value 2, which is half. Similarly, ZB1 is at most the probability that this guy has value 1, which is half. Right? I'm opening these boxes deterministically. I'm opening these boxes with probability 1. So this would have been multiplied by YA, but YA is 1. Okay? So that's why I'm dropping all the YAs, YBs. So this is just an LP on the Z's. There is some LP. What is its optimal solution? The optimal solution sets this guy to half, this guy to half. That's the best it can do. But what does that mean, right? If ZA2 is half, that means whenever I observe 2, I must have chosen the box. Right? Only then can this value become half. Right? And similarly, ZB1 being half means that whenever I see 1, I choose this box. Okay, that's what the LP is telling us to do. Open both the boxes. Whenever you see 2 here, choose this. Whenever you see 1 here, choose this. And the value you will get is 1.5. Right? But that's not feasible. Right? Because the policy is constrained to, any feasible policy is always constrained to choosing only one box. Right? And there is a small probability with which this box will have 2 and this box will have value 1. In fact, with probability 1/4, this guy will be 2 and this guy will be 1. In which case, any feasible policy can't choose both these boxes. But the LP doesn't care about that constraint. There's nothing that says that in some decision path you can't choose 2 boxes. Right? All it is capturing is something in expectation. Right? In fact, the optimal decision policy would be that if you see 2 here, choose it. Otherwise, if you see 1 here, choose it. And that will have value 1.25. That will correspond to setting this guy to half and this guy to 1/4. Right? But the LP doesn't. The LP has too few constraints to capture that. So it doesn't capture constraints across boxes. What happens if both these boxes have this value? Right? But that would be exponential complexity.
Why was probability to choose the box?
Open the box. Z is the probability of choosing the box. Y is 1 in, since k is 2, I can open both the boxes. I set y is to 1. So that's why I'm not multiplying by y here. The y is just assumed to be 1. But even then, even in that extremely simple case, right, the LP is not, the LP is still not giving us the optimal policy. It's giving us a relaxation of the optimal policy. Okay, so what do we do? So what do we do with this LP solution? We'll convert it into a feasible policy and bound the payoff, and we'll bound its payoff in terms of the LP optimum. Right? So the LP optimum is some upper bound. It ignores a lot of constraints, so it gives us a reward which could be larger than what any feasible policy could get. What we'll do is we'll take this LP optimum and convert it into a feasible policy and show that we don't lose that much in the reward. So what does the LP give us? Right? I mean, the LP didn't give us the optimal policy, so what did it give us? Right? So what the LP has are variables for every box. Right? So just focus on some box j. Right? The LP has a variable yj and it has variables zjvs. Okay? So what this is saying is open box j with probability yj. If you see value v, then take this payoff with probability zj divided by yj times fjv. So this is the conditional probability. Right? So if you uncondition it, the probability that you will open, observe, and choose will be exactly zj. So let's call this a single box policy, which is essentially saying if I focus on box j, what is a policy for this box? You open the box with some probability, you observe a value inside. If you observe value v, you'll choose the box with some probability. Okay? So that gives us a class of policies for one box. What to do with this box? So just to simplify notation, if I give you some policy for this box, right, which has those, which you can specify in this form. Okay, let OPJ be the probability that the policy opens this box. CPJ is the probability that you choose the payoff of this box, which is this guy, and RPJ is the expected reward you get from this choice, right, which is this guy. Now you can write the LP in terms of this simpler notation. What is the LP telling us? The LP is essentially telling us find one policy for each box. One feasible policy for each box, which opens the box with some probability. If you see something, choose it with some probability. Right? And there are only two constraints. That if I take all these policies and put them together, the expected number of choices made is at most 1, and the expected number of boxes opened is at most k. Subject to these two constraints, I want to maximize my expected reward. It's not capturing any other correlation or joint actions between these boxes. For every box, find me one policy, such that if I just put them together, these two constraints are satisfied.
So the size is the function of the maximum value of each of the distribution? Like,
What?
one of the constraints is overall V, so it is the size of the LP is a function of...
Yeah. So if you wait around a bit, I'll show you that the size of the distribution doesn't really matter. As long as you can compute some simple quantities for this distribution, it'll all be okay. Right? You don't really need to solve this LP. The final algorithm won't even need to solve this LP. This LP is more for thought purposes. Okay, good. Oh, sorry.
Maybe if you open a single box and if you see two different values at table, not only one. So how, even if you see 1,000, if you see 900, you still take both. So how it is captured in this thing?
No, from every box you only see one value. If I open the box, I see one value from that distribution. So there's some value inside the box, but there are no two. A box cannot have two values inside.
It may have. I mean, depends on what you see. I mean, it's for distribution, no?
No. The way I set up the problem, the box has some value inside it. It has one value inside it. What you know upfront is the distribution of that value. So the box cannot have two values inside it.
So for the second constraint for the first and second constraint, why is it smaller or equal but not strictly equal to 1 and k?
Actually, it will be strictly equal. I want to take the dual later, so that's why I wrote it this way. Where if you solve it, it will set it to equal. Yeah. Okay. So what does LP give us? So LP gives us one policy for each box. Let's call it a single box policy that tells us what to do with this box. It has only two constraints, that the expected number of choices made by all these policies is 1. The expected number of openings done by all these policies is k. And we know that since this LP is a relaxation, the sum of the rewards is at least the value of the optimal policy. This much we know. Right? But the point is that if I just put these policies together, it's not feasible. Right? I mean, it could be that many of these policies simultaneously decide to choose their boxes. Weird stuff can happen. Okay, so we want to convert this guy into a feasible policy. So suppose we could solve this LP. Let's convert it into a feasible policy. I'll show later that you don't even need to solve this LP. Okay, but suppose you solve this LP, you got this stuff. Let's convert it into a feasible policy. So this first step is I'll give you a very simple algorithm. Just order the boxes arbitrarily, 1, 2, 3, 4 somehow. Okay, and consider the boxes in this order. Suppose the policy encounters box J, then with probability 3/4, just skip this box. With probability 1/4, this is where I'm sort of keep in mind to ignore my constants. Right? With probability 1/4, execute what the LP is telling you to do, which is this policy Pj. So what does the Pj do, right? I mean, with some probability, it decides to open this box, and if it opened and observing some value, it decides to take its payoff. If the policy decides to take the payoff, then take this payoff, stop. Because you can't take any more payoffs. Okay? Else, move to the next box. Again, do this business. If you have already opened k boxes, then stop. Now, this policy is feasible because you're never going to open more than k boxes, and you're never going to choose the payoff from more than one box. There's a very simple way of converting what the LP gives you into something that is feasible. Now, what we want to argue is that this is okay. That this gives you some approximation to this guy opt. That the reward that this whole thing gives you is at least some factor of opt.
Why wouldn't you open k boxes every time if it's just, why would you stop before opening k boxes?
You won't stop because you could have the policy Pj that you execute could have chosen the payoff of. You could go till you open k boxes. It doesn't improve the analysis. So what I'm going to analyze, you're right. I mean, they're like somewhat dumb. In fact, there are better ways of doing stuff. Yeah.
I don't mind ignoring the 3/4, but could you just tell us sort of where
it'll come? I'll tell you where it comes. I'm going to analyze this thing. Yeah.
So when you reach k, you stop and no payoff?
There could be no payoff. I mean, you could have opened boxes and you could have seen zeros everywhere, or you just choose whatever the max you observed so far. But for the way I describe this algorithm, this is exactly what I'm going to analyze. If you implement it, you can implement it in a much better way than what is described here. In fact, there is no reason to order the boxes arbitrarily. You can order them more cleverly than arbitrarily. Right? There are a whole bunch of, this analysis is very slack. Okay. So let's define some random variables for the execution of this policy. So let Oj be a random variable, which is 1 if box j is opened. Let Cj equals 1 if the final payoff that is chosen by the policy is from box j. So the policy reaches some box I if two things hold. So these are both 0, 1 variables. So the number of, so all this is saying is how many boxes were chosen before j. So if this value is 0, then the policy, that means nothing was chosen till the policy reaches I. this is the number of boxes that are opened before I. If less than k boxes are opened, then the policy can still continue. So the policy reaches box I, it didn't stop if this quantity, the number of boxes opened so far is less than 1, and the number of boxes opened so far is less than k, and the number of boxes chosen so far is less than 1. Right? But these are all 0, 1 random variables. This is a complicated way of just saying that this guy must be 0 and this guy must be at most k minus 1. Okay, and what we'll do is lower bound this probability. What we'll show is that the policy reaches box I with sufficiently large probability for every box. And here is where we'll just use Markov's inequality. So the probability that this is a random variable, probability is less than 1 is at least 1 minus the expected value of this random variable. Probability this random variable is less than k is at least 1 minus the expected value of this random variable divided by k. This is called Markov's inequality. I'm not going to prove this. I mean, this is standard. Okay. Okay. So now what we need to do is calculate this guy and this guy. Right. So the probability that the policy reaches box I is the probability of both these events happening, which is at least 1 minus this guy by Markov's inequality, just by union bounds. Okay, so we need to calculate this guy and this guy. Okay, what is expected? So what is the expected value of Cj? Right, this is the probability that the policy chooses something from box. This is the expected value of Cj given that box j is not skipped. I mean, you reach box j, you could skip it. So you have to not skip it, you have to actually go inside. Times the probability that the box is not skipped, right? So this is just calculation, and probability the box is not skipped is 1/4. With probability 3/4, I'm just skipping the box. Right? Condition on not skipping it, I'm going to execute this policy, and that chooses the box with probability CPJ. So this is the LP value. Okay, condition on not skipping it, I'm just going to execute the LP. So the LP tells me to choose the box with this probability. So this guy, this random variable, is at most this guy. It's clear, right? I mean, probability 1/4, I'm not skipping. In fact, the probability is going to be less than 1/4 because I may not even reach this box. Right? And similarly, the probability that the box j is opened is the probability that it's opened given that it is not skipped times the probability it is not skipped. Probability it is not skipped is 1/4. Condition on not skipping it, the LP tells you to open with this probability. So it's this guy. It's going to be even less than that because you may not even reach this box, but whatever. It's an upper bound. That's all we want. And this is where the skipping and the 1/4 is coming in. Yeah. So now just plug those values in. This is the probability the policy reaches box I. This is Markov's inequality. Just plug those numbers in here. Right? So you have this 1/4 because of the skipping business times this guy. Now the LP tells you that the sum of all these values is at most 1. The LP tells you the sum of all these values is at most k. So the LP is telling you that all this guy is at most 2. So the LP so just plug that in here. It will tell you the probability that the policy reaches any box I is at least half. Okay. All we have used is Markov's inequality. That's it. And you just use the LP constraints in saying that this guy is at most 1 and this guy is at most k. Okay. And this 1/4 is just to make sure this thing works out. You have to skip with sufficient probability to make this guy large.
So if you had 3 constraints, you would put down a 6th out there or something like that?
Yeah. It blows up in the number of constraints. Okay. So now what we do is say that, okay, what is the reward of this policy? By linearity of expectation, the reward of this policy is the sum of the expected rewards it gets from each box. Okay. When will it get a reward from a box? It has to reach the box, not skip it, and do something with the box. Right? So the probability that the box is reached is half, at least a half, times the expected reward from this guy. So it's half times the probability that the box is not skipped, and given that both of these things have happened, it's going to do something with the box, and it'll do what the LP tells it to do. Right? So it's at least half times 1/4 times whatever the LP is telling it, so it's going to be RPI over 8. So from box I, from any box I, the expected reward the policy gets is at least what the LP gets divided by 8. Cool? Right? And for this, we crucially needed that like every box is reached with sufficiently large probability, and that needs us to skip boxes with sufficiently large probability. So it's These are the best constants you can plug in to make this work. Yeah.
So this is also saying that you get 8 approximation for take it or leave it offers not just maximum of k open?
Yeah, maximum of, even for take it or leave it. In fact, the 8 is not tight. I mean, you can get 2. This. Okay. So since I only have 7 more minutes, so so just after this point, you just use linearity of expectation. From every box, I'm getting 1/8 of what the LP gets. By linearity of expectation, the total reward of my policy is at least 1/8 of the LP value. Okay, so that gives you an 8 approximation. The constant is bad. You can improve it to 2. Whatever. Okay, but this policy is like sort of adaptive, right? I mean, it is not really, but let's just show, okay, what is an adaptive, to show an adaptivity gap, right? I mean, what we'll do is we'll look at this LP and say, okay, look, let's not solve the LP. Let's see if this LP has some very simple structure. Okay, let's look at the LP again. It's blah. There are 2 constraints. I don't like 2 constraints. Let's write it as 1 constraint. Let's just add the 2 constraints. Okay. This is just saying I just divided this second constraint by k, added it up. Okay. This is an even weaker LP. Right? I don't like this number 2. So since this is an LP, I can just scale everything down by a factor of 2. It loses some 2 in my objective. Now 1. 1 is nice. Again, this is all very loose. There are better ways to do these things. Okay. So this is a very weak LP. This value is at least opt over 2 because I've scaled stuff down by a factor of 2. Okay, good. I have only 1 constraint now that connects the different j's together. Everything else is within a j. Right? I have 1 constraint. The nice thing about 1 constraint is I can take the Lagrangian. Okay, so let's define some dual variable w here. And let's put that in the objective. So this is what I'll get. What is this guy? I'm maximizing. So I'm maximizing something, which is a sum over j, but the constraints are only for each j separately. There's nothing that couples the j together in the constraints. Okay. So now if you want to solve this, you just solve separately for each j. There's nothing connecting the j together. So if I focus on a particular j, what is it solving? It's maximizing this quantity subject to pj being feasible. But what is this quantity, right? If I look at it, it's reward. If I open the box, I'm paying w over k. If I'm choosing the reward, I'm paying w. Okay, so that's maximizing reward minus cost. The cost for opening is w over k. Cost for choosing is w. I want to find that policy for this particular box that maximizes reward minus cost. And this policy has a very simple structure now. It's like one box. What can I do, right? I can either open the box or not open the box. There's no reason to do stuff probabilistically. Right? So just take the better of 2 options. Suppose I don't open the box. Everything is 0. I gained nothing. I lost nothing. 0. Open the box. I paid w over k for opening. If my reward is bigger than w, I might as well take that reward because I'll obtain the reward and pay w, so that's a positive number. So the net value would be the expected reward minus all this cost. So it's a very simple policy, right? I mean, it will in fact say that there's this threshold w. Okay, open the box. If the reward is more than w, choose it. That is 1. The other option is to just not do anything. Take the better of these 2 solutions. So here is a case where if you take the dual, take the Lagrangian, it's giving you a very simple policy. So why is the Lagrangian useful? Roughly speaking, because of strong duality, right? The solution to the original LP corresponds to choosing a w such that this quantity is equal to 1. As I increase this penalty or this cost, right, the w, then it's less and less likely that the policy will even open a box or choose something because the cost is too high. Right? So there'll be some point where, as I increase w, there'll be some point where this quantity, the expected cost plus expected cost becomes equal to 1. Okay. At that point, by strong duality, the value of the Lagrangian must be equal to the LP value, which is opt over. So you can solve the LP by essentially doing a binary search over w. Right? For every w, you just compute these policies for each box, which have a very simple structure, and now just do a binary search over W to find that W at which this constraint is satisfied. This is roughly speaking. I mean, there are some technicalities. There could be two Ws. For those who are familiar with this technique, this doesn't exactly work, but roughly speaking, this is the idea. Okay, so now what it shows, the moral of the story is that this LP optimum has a very simple structure, right? It has some threshold W, okay, and for that W, it computes these single box policies, which either doesn't open the box, or if it opens the box, it chooses it if the reward is more than W. Right? The important thing is that the decision to open the box is deterministic. The policy either doesn't open the box or opens the box. But I have this LP constraint which says that the number of boxes opened can be at most k, right? Which means that if I take this LP optimum solution, it must have opened at most k boxes. The number of j's for which it would have set this, for which the policy would open the box is at most k. I mean, that's why I scaled it down by a factor. I mean, so if you look at this constraint, right, I'm saying this OJ is like a deterministic value. It either opens the box or doesn't open the box. This guy is 1, so this OJ must be at most k. Sum of the OJs must be at most k. So the LP optimum is telling you, okay, here are k boxes, at most k boxes, and their yj's are 1. Okay. Now, what I do is suppose I just open all those boxes. Okay. The value I get must be at least what rounding this LP will get us. The rounding is only worse, right? But the rounding is getting us, it lost a factor of 8, and I lose another factor of 2 because I scaled down by a factor of 2. So it's factor of 16 off. But if I open all these boxes, I have a non-adaptive policy. I just solved this LP for this value of, I solved the Lagrangian from this value of W. It's telling me, okay, here are k boxes for which yj is 1, right? And I just go ahead and open those k boxes. That's a non-adaptive policy, and choose the max, right? If I do this complicated LP rounding, it is only worse, right? Which means that this non-adaptive policy must have had value at least opt over 16, which means the adaptivity gap is 16. This is a horrible constant. You can improve it to 3. But is the idea clear that if once you take the dual, right? I mean, this dual has such a simple structure, and by strong duality, that will tell you that the original LP also had very simple structure. You don't really need to solve the LP. You just have this threshold, and just decide, okay, for each box, should I open, not open, right? And just do binary search over the threshold till it satisfies the LP constraint. That's it. That doesn't need you to write this complicated LP. For every threshold, I can easily compute what the expected value of the policy is. And so it gives you a policy with very simple structure. And once you have this policy, you can see that, okay, the decision to open every box is deterministic. There's no yj is not a fraction. And once you have that, what you have is a non-adaptive policy. That's it. And this kind of idea I'll show you again in the next second half of the talk, where the duality is powerful in stochastic optimization for this reason, that once you have the dual, you can reason more about structure. Yeah.
It is an explanation. It's not factorial.
Sometimes the way we do approximation algorithms, this could be, your question is very valid, but yeah, it is an exclamation.
Yeah, so you said that this doesn't exactly work. Why is that?
For the simple reason that there may be no setting of W for which this guy is exactly 1. I mean, maybe for some value it's less than 1, and make W slightly larger and it becomes greater than 1. So the LP optimum would correspond to like 2 very close by W's. It's a convex combination of 2 very close by W's and the Lagrangians for those. But that's a technicality. I don't want to dwell too much on it. In fact, if you want to show an adaptivity gap, you don't go this route. In fact, there's a very different setting of dual variable that directly gives you 3. But the basic idea is this, that the Lagrangian has very simple structure.
So where does the submodular solution fall with respect to this?
So this shows that if I compute the optimal, so suppose I do the greedy algorithm, right? That is 1 minus 1 over E against the best non-adaptive solution. But the best non-adaptive solution is only factor 3 off from the best adaptive solution. So overall, it's 3 times E over E minus 1. In fact, what you can show is that it's this whole LP business actually gives you the non-adaptive solution directly. You don't need to actually do greedy. you do this threshold business and search, what you get is a non-adaptive solution.
Returning to a question before, if you are adaptive but it's supposed to take the last one, so then it doesn't work. I mean,
then that's Matt Stock. That's roughly speaking Matt Stock. That's the profit inequality setting. In fact, a similar thing will work there as well.
You have lower bound on the gap between adaptive and non-adaptive?
No, I know it's at most 3. No, I don't have a lower bound on. It'll be at least some constant, but I don't have a tight result.
So in the previous algorithm, since you know the distribution, how would you set the boxes, order the boxes?
You would order it in, you just do knapsack, right? I mean, you order it in decreasing order of reward divided by the cost. So in fact, if you look at it this way, right? I mean, you just do reward divided by the cost. Expected reward divided by the expected lab. Choose that ordering and you can do something better. You won't get 2, you'll get 4, I think, because you have 2 constraints.
Since the distribution is fixed in the beginning, is it possible that the adaptivity gap is arbitrarily close to 1? Even though the approximation gap can be some constant, as you said.
No. The adaptivity gap, there are stochastic optimization problems. I mean, even if the distributions are fixed, the non-adaptive policy could be much worse than the adaptive policy. So it's you can easily construct problems where the adaptivity gap is bad. For this, it will, I think, be at least a constant.
So, Kamesh, the example you gave at the beginning, with just these 3 boxes.
Yeah. That had a
3.9 versus 3.7.
3.9, 39 versus 37.5. That was, yeah. It will be, it can be bad even with fixed distributions.
Do you have examples in this mixed value kind of problem where actually describing the optimal strategy requires exponentially k description size? So it may be that they all have succinct descriptions.
Open questions. So that's a. I don't have proofs beyond NP hardness for any of these things. I mean, showing that. So there are, if you have, you can come up with sort of contrived Markov decision processes which are like p-space complete. Right? What you're saying is, I mean, is this problem p-space complete essentially, right? But for these sort of natural decision problems, I mean, even for, I'll show in the next talk, like even for Bayesian auctions or Bayesian pricings, showing its NP hard itself is like a paper in itself. And for these, I don't know if, I mean, for the non-adaptive policy, I have an NP hardness proof, but I don't have anything more than that. So that's a very interesting open question. The more simple you make the problem, the harder it is to show these kind of results.
What you might have already answered. So what's the best adaptive policy constant that you know for this problem?
For adaptive, I think 3 is the best that I know. So in fact, the adaptivity gap and the approximation, both 3 is the best. Yeah.
Even like adaptivity does not.
No, that's another interesting open question.
Okay, let's thank Kamesh and take questions.